The last video we did some very simple like reliable data transfer protocols, and we were using a non-pipeline process, so it was just like stop and transfer. I think that's what it's called, right? Stop and transfer. I'll just yeah. Wait a second. Yeah, so it's called stop and wait. So once you send it, you just stop and then you wait. Okay. Uh, Now we'll go to something which uses pipelining. So we'll be using go back n. That's the protocol's name. And it works like this. So on the sender side, what happens is that you keep an array p, which is basically it's like all the packets that you have to send. Whenever you don't need a packet anymore, you can just delete it from the array to reduce the cost. But you can think of it as some sort of linked list or some virtual array. But yeah, so basically this, or some sort of associative array, that's probably better. So what will happen is that whenever you say p of n, where n is a sequence number, it will give you the packet that you want to send, right? And then whenever you send a packet, you will send the packet as p comma n. So the packet with its sequence number, right? So this is what's going to happen on the sender side. So the way this actually works is that on the sender side, you have all these packets lined up that you want to send. You have already sent some packets. Now the next packet that you would like to send is this. So this isn't there yet, like some application layer or some upper layer will actually give you some data to fill this in with, right? So this is your array p, by the way. This whole thing is your array p. So it will give you, and this is like already filled. I mean, it may not be filled in the actual implementation, but you can logically assume that it is filled. So now if you actually get a packet, so if you want to do send or reliable data transfer, some packet p, right? So you get some data. What do? First, you check if you actually have space. So what will happen is, from this base b, you'll have some window of size n. So all the way from this to some b plus n, maybe this thing is b plus n, excluding this, you can send packets. So all of these slots you can fill up in that array, right? So whenever the upper process wants you to send a packet, what all you have to do is just send it. Yeah, it sounds easy, but what really happens is, if that b thing is so if like the so I mean, okay, the thing is, you would probably already have some packets that you already sent, but they're not acknowledged, so they are sitting in here like this, and this is actually the next slot where you want to send the where you want to store this new packet. So the reason we are storing it is because in case your packets aren't acknowledged, you would want to send all of it again. Remember, it's a pipeline thing, so you don't wait for acknowledgement for every packet. You don't do like, okay, once I'll acknowledge this thing, like I know that this thing is there, then I'll send the next packet. No, you just send the packet as they appear, right? But you still have like some sort of limitation. You'll only be having some n packets, window size packets, on the wire at any given moment, right? So this number, which is called the next sequence number, is the sequence number that you'll assign to the next packet that you want to send. So somebody gives you some data, right? What you as a sender will do is that you'll fill this slot. Of course, first you'll check that do I even have space. So if the next sequence number turns out to be bigger or equal to this p plus n thing, so if n bigger than or equal to p plus n, we'll just say, I reject your offer. I don't want to send the packet because I'm already like my plate is full. So it will just be like, don't do anything. Okay, otherwise what will happen is, you'll get this thing. Now you have to store that, so it's like store it, and then you send this thing. So you do some unreliable data transfer, right? Just like shooting an arrow. Not really sure if it's going to hit, but with this p thing and n, so you basically packetize into some protocol data unit, which has so this is basically the SDU, the service data unit. and you'll like fill up all the header fields and everything, and then you'll send that thing. So that's the unreliable data transfer. And I'm just writing it like that, but it's actually more complicated. Yeah. Okay, so that's more or less all you really have to do. Just let me check, is this the thing? Yeah, so you just do the data transfer, you fill this capital P array up, and oh, you also do some timer and increment. So since now you have filled this up, you have to increment n, that's kind of obvious. So just do n plus equal to 1. But at the same time, if this was like the first packet that you sent, that if b was actually equal to n, that is to say, you had not sent any packets before, in that case you'll also start a timer which will use for the timeout event. So that's supposed to happen before the increment, because yeah, the current like sequence that we assigned to this packet, that's what we want to compare to b. So if b was equal to n, in that case you'll just start the timer, and in any case you'll just increment this thing. So if b is not equal to n, well, the timer is already going on, so you just keep it going, right? So that's what happens when you want to do some like this RDT thing, right? Reliable data transfer. That's just like for sending the packet. Now you also have other things. You have acknowledgements and you have timeouts. So let's think about what happens on timeout. So in case of timeout, right, one thing is like you'll have to restart the timer. So you just start the timer, because it has to then account for the next thing. And so when you encounter timeout, what it's basically saying is like that the first packet that you send, the packet which is positioned at this B thing, you didn't actually get acknowledgement for that at all. But this is slightly a dumb protocol. It doesn't care like if these were acknowledged or were not acknowledged, if they reached whatever. So what you'll do is you'll just, okay, so also the reason why we're thinking of that is because the acknowledged numbers, they are cumulative. So if you get an acknowledgement, what it's saying is that you have like that the receiver has received all the packets up to here, not that it has received only these two packets or something like that, not thinking about this packet. That isn't what the receiver will do. So it's cumulative acknowledgement, and that's why you can do this. So if you just haven't received then all you can assume is, okay, this thing didn't reach, and because that didn't reach, these were not counted, so I'll have to send this. But since I'm a pipelined protocol, I'll set everything in fact. So it's like for some sequence number going from b all the way to n, like exclusive, so n minus 1 inclusive, you'll just send the packet. So just like udt get whatever the packet is, so pm, and then packetize it. Actually it's probably already packetized, but just for the sake of it, packetize it, like create a pdu, that's what I'm saying, and then send it, right? That's what you'll do. Yeah, and that's a simple timeout. I guess that's it, right? That's what a timeout is. Just let me check. Yeah, that's more or less that's what a timeout is. Now the final part is when you want to receive acknowledgements. So I'll just say receive packet, because these packets will contain acknowledgements. Yeah, so more than acknowledgement, also contain a number that describes. So in TCP you actually have something known as acknowledgement number, which is slightly different from what I am going to write and what this book writes for this section. So this is going to be the so the number that you'll get is basically going to be the last packet that was received on the receiving end. Yeah, so you'll just be like, okay, you've got some packet q, from that you'll extract the acknowledgement number. So a equal to like extract or get acknowledged, I don't know, get ack q, so that's the acknowledgement number. Now if this is what you're expecting, and you're expecting b, by the way, so if this is what you're expecting, that's good. And so okay, if b is filled up, you go to the next one and so on, right? So if this is more than b, what it's essentially saying is like, okay, all these packets were already there on the receiving end, and you just send the acknowledgement for this rather than sending it for each of them. Although it will actually send it for each of them, it's just like they may be lost along the way. So now that you have this, that okay, all the way till that it's done, all you have to do is just say B is equal to, so like update it, the base basically as whatever the acknowledged number is plus 1. So because A is till where you have acknowledged, so that plus 1. Yeah. What happens if A is less than B? So A plus 1 is less than B. Then that's a messed up situation. In which case you shouldn't increment it or whatever. But then again, if like A is less, that's just not gonna happen, because then how did you move your B before that? That makes no sense at all, right? Could you be sending multiple acknowledgements for the same thing? Probably yeah. Probably yeah. So you also have to think of that actually. Let's see if that is in the FSM that they've done. No, they've directly like just done like base equal to get acknowledgement receive packet plus 1. So that's messed up, because I think it should also have a check that if the acknowledgement number you got is lower than what you're expecting, then you probably shouldn't be doing anything, right? Yeah. But how could it be lower than what? Because before B everything is already acknowledged. Yeah, but that doesn't mean that you can't get multiple acknowledgements. True, you can get actually multiple acknowledgements. So you should have that. I don't know why the book doesn't have it. Huh. Well, this is kind of messed up. But anyway, so just like if, you know, if A plus 1 is like bigger than B, because if it's equal to B, then okay, if it's equal to B, it seems like this thing is acknowledged. No, that's if A is equal to B. If A plus 1 is equal to B, that's like, okay, the previous thing is acknowledged, which doesn't make any like difference. So if this thing is bigger than B, then what you'll say is like, okay, B, you update it as A plus 1. Yeah, that's what you'll do. That's acknowledgement. Now, yeah, you also have to do this other thing, that if this is like the first packet that you got an acknowledgement for, then sorry, if this is the last package that you got an acknowledgement for, that is the next sequence number, you're already caught up to that, right? So like now whenever you will get a data you want to send on the sender end, it will be like your first packet in this stream, more or less, right? So if that happens, which only happens if your B thing is like equal to N, right? It has somehow become so that you have transmitted every single packet and acknowledged all of them, right? So it's like the job that you're assigned is done. In that case, you can stop the timer, because the next time the timeout event will go on, it makes no sense. Like it will just start a timer again and will keep going. That doesn't make any sense, right? Yeah. So you just stop the timer over there. Okay, so that's more or less that's more or less the thing. Oh, of course, you also have to take care of corruption, because if like Q is a corrupted package, what that means is, that's problematic. So you just like discard it. So if corrupt Q, then you say, okay, skip everything. We don't really care at this point. So yeah, that's what happens on the sender end. What happens on the receiving end? Well, the receiving end just gets these packets and it has to send back the acknowledgement. So of course, if it gets corrupted packages, it like doesn't take that into account, just sends back the acknowledgement for what it already has. Cumulative acknowledgements, by the way. So you do some receive packet, and this is on the receiving end, by the way. Receive packet some P, you'll extract the properties of this thing, so you'll get a sequence number. So M you'll say is like get sequence. Okay, before any of that, if it's corrupted, well, good, just skip. So if corrupted P, then so what this receiving end does is that it actually maintains two things. First is like the expected sequence number, so the next packet it's expecting, and the second thing it maintains is the last transmitted packet, so the packet last transmitted by the receiver itself. Right. So it just has like that packetized thing stored so that it can keep sending that. So if the packet it sees is corrupted, it will just send that. So it will like transfer Q, where Q is the last sent packet by the receiver, which is also like an acknowledgement for whatever happened before, right? because it's just like it's got some corrupted thing, so it doesn't know what to do, so it will be like, okay, whatever, I'll just send the acknowledgement. Yeah. So okay, that's cool. If it has, I mean, you can also not send it because then the timer event will take care of it. But yeah, better send it, right? True. Better send it. Okay, so if corrupted, just do that. Otherwise, if it's not corrupted, in that case, you can start extracting stuff. So you can extract the actual data, which I'll just write as P, the sequence number. Actually, before any of that, you just like get the checksum. So checksum is just like get checksum from P. You also need to get, what is it called? I was gonna do something. Oh no, this is in the checksum that you'll use. Sorry for that. Um, yeah, actually, the checksum that we use is for the packet that you'll send. So you don't really use P in that. Yeah. Okay. So all you need is just the expected sequence number, and that's more or less it. Fine. That's what you need to send back. So before doing any of that, you will obviously deliver the data. So it'll be like deliver this packet P. Uh, yeah. Oh, that only happens if it's actually the correct expected number, right? So you'll get the sequence number for this. So M is equal to get sequence from this P thing, right? Am I doing things correctly? Yeah, okay, yeah, I'm doing things correctly. So if this thing is not the correct thing, so if M is not equal to E, where E is the expected sequence number, you'll be like, okay, I don't care, I'll just send the data back because, like, yeah, whatever. Else, if it is the correct thing, then you'll start delivering it. So you'll be like, deliver this. Also, now you want to update Q because now you want to send an acknowledgement that yes, I've received this new packet that you sent me. So you'll be like, Q is just the acknowledgement, which will be like, I don't know, make packet um, with the expected number. So it's just E. Yeah, because this is what you got just now. So you'll just send this back to DTQ, right? And of course, you'll increment E because now the next thing you'll expect is the next number. So far nothing problematic. And over here, the checksum is actually like for Q itself. Yeah, so the book is a bit confusing because I don't know why it's using that. Anyway, you also kind of have, so in the corrupt thing itself, you are using the checksum for P and all that. So the error correction takes care of itself. So that's the go back N protocol. Yeah, I guess this is it. I'm not missing anything, am I? No, it's fine. So it's kind of easy, like on the receiving end, it's rather easy, isn't it? Also, so initially, Q is set to be the, you know, is set to be this thing. So initially, Q is set to be make packet 0, where 0 is like the initial expected number, but then it just straight away goes to 1. And you obviously also send this, right? Yeah. Right. So like if you don't get anything back, then what you can assume is okay. Uh, actually, yeah. If you don't get any more data from that, then you probably shouldn't be sending anything because it has stopped or something like that. Yeah. Okay. So that's cool. I mean, it's the sender's job to think about whether or not the packet was correctly transmitted. All the receiver has to do is just tell that, yeah, the packet is here or it's not here or whatever. Right. And this Q thing, I mean, it's not having information about corruption, not corruption, but then again, its expected number is lower. So by that logic, it's something like a not acknowledged, the NAK thing that we were initially using. Alright, so that's it for this video. I'll do the simple repeat algorithm next. Right, bye.